Welcome everyone to our first virtual Data Republic meetup. This is a bit of background before we start behind Data Republic is that some of my colleagues at Data Republic founded the SRE Republic group back in March. Some of you might already be aware, last year, which is more a platform for SRE and DevOps professionals to network, learn from and share experiences and advice with peers. So off the back of that, I noticed a gap for a data-specific meetup. So here we are, first Data Republic virtual meetup. Introducing our line of speakers, we've got Lionel, who's the first speaker, who's an engineering manager at Zalando, and Peter, who's the data engineering team lead at Quandoo. Both incredibly experienced and successful tech and data professionals. I'll turn you to our first speaker, Lionel.
Thank you. Hi, my name is Lionel. I'm engineering manager at Zalando. Yeah, we're going to talk about writing a resilient event consumer one incident at a time. So what does that mean? And why are we talking about this? So as I said, I'm engineering manager at Zalando, and my team is working on the central event streaming platform. It's called Makadi. It's actually open source. There's a link at the end of the talk, but you can check it out, makadi.io, if you're interested. It's basically based on Kafka, but it's got a bunch of added features that we find quite useful. And I've been with the team for almost 4 years by now. But I started as an engineer, so I contributed to the code, and then about a year ago I started transitioning to management. But the point is, we have been running this central event streaming platform based on Kafka at Zalando in production for about 4 years. It started a bit before I joined. And in that time, a bunch of incidents happened, right? So we can see that event streaming or event-driven architectures are very, very nice, very interesting. They have a lot of promises and they achieve a lot of results, but that doesn't mean that publishing events and consuming events is trivial. In fact, it is not. Many things can go wrong, and often they do, and when they do, incidents happen, just like in many other complex systems. So in order to make this talk interesting, I thought we're going to start with an event consumer that's fairly simple, nothing too fancy or too complicated, and then we're going to go through a series of incidents. The incidents are not really real, but they're based on the incidents that have happened a lot at Zalando. So it's kind of a lie, but it's only a little lie because there's a lot of truth behind it. And we'll see through the series of incidents, I think we have 3, then we'll make the event consumer a little bit better. And hopefully for you, you will learn a thing or two, and maybe it will even be entertaining. And you will learn about how to monitor, alert, and what to think about when you get started with event-driven design. Progressively will make it better. And I'm going to need 2 volunteers. If 2 people could write in the chat that they volunteer for the talk, there's nothing to do, actually. I just need 2 names. So we have Subin and another one, Danny. Also pronouncing it correctly. So thank you, Subin, and thank you, Danny. You're going to be my guinea pigs today. I hope you don't mind. So I'm going to get started immediately with the event consumer we're going to build. So let's imagine that this is extremely unlikely and it's not going to happen. Next week, next month, next year, Zalando decides now we sell fashion online. For those who don't know Zalando, it's a European fashion retailer online. Maybe next year we decide we want to also sell bicycles. Why not? The weather's nice, people like to cycle. I don't know it will actually happen. But Subin will be the engineering lead for the team that will build this event consumer, and Danny is his boss, because I said so. And so one day Danny will tell Subin, like, come on, bring your team together. What I want you to do is to write an event consumer that will consume the events from all the orders that come into the shop and enrich them with additional information, and then publish the result also to the event streaming platform. So fairly typical way of building a service in event-driven architecture. You consume something, you enrich it, you republish it, and then another services, or maybe several services downstream, can then consume the result and do something with it. So we can look into it. What would it look like? Basically, there's an input on the left, there's an output on the right. The input that the service that Subin's team will consume basically has the name of the bike, in this example, the type, the model year, a series of options that the customer has chosen, like maybe the color, the size of the frame, whether or not they want reflectors, or what kind of pedals, and all sorts of things you can add to the bike. And of course, a customer name and a customer address. In reality, you'll have a bit more. You'll have like billing address. You have maybe delivery option and a bunch of things, but let's keep it easy. And the output is quite simple. Basically, you copy the exact same thing, but you add this enrichment, which is a list of parts: a frame, something about wheels, brakes, and maybe a bunch of others. Right? There's probably like 100 parts or something in a bicycle these days. So that's basically what the service needs to do. But then it tells Subina, okay, I want you to build this service, but you should be able to handle about 10 orders per second. 10 orders per second. That's about the number of orders we get. But in fact, just to be sure, you should be handling 20, right? It's actually, by the way, a very good idea when you write your consumer, that the consumer can handle events faster than they come in, because one day, eventually, inevitably, there will be a problem and you'll have to catch up. If you can only go at the speed of the publisher, you will never catch up. So it's good to be able to consume faster than the publisher publishes. And then he also tells Subin, do you have an SLO? I want that over the course of a month, 99% of the orders are processed within 1 minute. And now Subin goes for it and said, okay, I'm going to do it. All right, so that's the event consumer we're going to build together. But before that, I want to say a few words about Nakadi. We're going to use Nakadi as an example, but in fact, this talk would also apply to Kafka. It will also apply to Kinesis, and maybe other platforms, but these ones are the most the closest to Nakadi, certainly. If you're at Zalando, you'll probably use Nakadi. If you're not, it's unlikely, although if you are, because it's open source, please let me know. I'd be really interested in knowing that. But the talk is not about telling you that you need to set this particular value to that much and that one to that much. It's more general principles of what is something you want to look at and to be careful of when you write a production-ready event streaming system. Use a production event streaming system and write production-ready services that use it. So Nakadi at Zalando, what does it look like? In a few numbers, I picked a random day, not that long ago, and these are approximate numbers, of course, but we handle about 10 billion messages published on a typical day, so that's quite a lot, which represents about 34 terabytes of data, right? So for those who do the math, I think it's about 4 kilobytes per event, if I'm not mistaken. We had 40 billion of messages consumed, not published, there's a typo, and that represents 130 terabytes of data consumed in the period of 24 hours. And we have over 2,000 active event types. An event type in Nakadi is roughly equivalent to a topic in Kafka or a stream in Kinesis, for those who know about these systems. So basically, it's sort of a unit where you send events that have some sort of commonality, like orders or clicks or movements in a warehouse or something like that, right? Event types also have a schema, we also have authorization and a bunch of things. So that's kind of what it looks like. And just to give you a very, very quick overview of how we deploy it, this is the deployment for Nakadi at Zalando. So on the right-hand side, you can see there's a Kafka cluster with Zookeeper. That's basically where the messages actually are stored. And then in front of it, there's Nakadi that provides an HTTP API that you can use to publish events or messages and consume events or messages, and a bunch of other things like create event types, update schemas, change authorization, get some KPIs and monitoring, etc. Nakadi uses a Postgres database as well as its own Zookeeper to keep the track of the consumers. And in front of Nakadi is Skipper, which is another open source project from Zalando. It's very useful. It splits the traffic between the different Nakadi stacks that we have at the moment because they have different traffic profiles, and it's useful to separate them. You can do a bunch of other things, HTTPS termination, authentication, and a bunch of things. And of course, all the way to the left, the users, of which we have very many. And most things except Kafka actually are deployed in Kubernetes at the moment. Now, In the Zalando event streaming platform, there's additional few services that are not mentioned here because they're kind of not exactly the point of the talk, but we have a SQL over stream engine where you can run continuously some SQL query that does joins, projections, and filters. We have Nakadi Archiver that sends the data from some event types to Zalando's data lake so that you can get the data for historical data for as long as it is kept there. And you have a new project which is Nakadi 2X, basically it's very similar to Kafka Connect, where you can decide, okay, I now want to materialize the events from this event type into a Postgres database, or into Elasticsearch, or DynamoDB, or whatever you like. And instead of having to write your own Nakadi consumer and deploy it and run it in production, you just write a couple manifest files and there you go, we deploy it for you. So that's kind of how it goes, and that's the context in which Danny and Subin will be writing their event consumer, right? So how do you consume events with Nakadi? You use, it's again very similar to Kafka. I need to mention it because it's important for the incidents we're going to look at. Basically, you create a subscription, and one consumer has one subscription, and in the subscription you will see all the events. This is something that is common to Nakadi, Kafka, and Kinesis, is that you can have many consumers for each event type stream on topic, and each consumer will see all the events. So you have your subscription that you've created, and you open a connection, and Nakadi starts sending you a series of events. And you can choose some parameters, like the maximum number of uncommitted events, the batch size, to kind of get an idea of how many events Nakadi will send you. Then you enter a loop where Nakadi expects you to commit the offset, so the checkpoint, to tell Nakadi, well, I have processed these events until this point, and then until that point, and until that point, constantly, so that whenever you get disconnected, which will happen, and then once you reconnect, you will start getting events from the latest committed offset. So you don't have to keep track yourself of where you are in the stream. You just tell Nakadi regularly, I'm here, and it takes care of everything. This commit offset in Nakadi also serves as a keep alive, so that Nakadi knows that the consumer is still there and consuming. Otherwise, it will also close the connection. So let's build that consumer, right? So we can have a look. We want a very simple consumer. There we go. That's a very simple diagram. So we have Nakadi on the left and the order processing service in the middle. And on the right, we have a bypass service that is already there, that's taken care of by another team under that. So now the order processing service that Subin's team is going to build consumes from an event type called orders.incoming, calls a REST API to the bypass service to enrich the event, and then publishes the result to orders.enriched. Fairly simple. And so Subin's team spent a few weeks working on that, and eventually they're ready and they go. They go to production, and here's everything is fine, of course, at this point, and these are the graph of unconsumed events. You can see there's between 0 and 5 unconsumed events. Everything is fine. The service is running good. No problem, right? Fast forward a few weeks or a few days. Let's say a few days. Fast forward a few days, of course, if something goes wrong, inevitably. Luckily, it happens during working hours. And so Danny calls Subin and says, yeah, we have a problem. No, what's the problem? Oh, we've lost events. What do you mean we lost events? We can't have lost events. We did. There's a problem. We lost events. Some customers are not getting their orders fulfilled. So what happened? Well, nobody told Subin, and in fact nobody told Danny, but instead of 10 orders per second, the number of orders per second has increased to 50. Now we know that Subin's service can only handle 20 orders per second, and therefore every second a new 30 orders accumulate in the backlog, right? And unfortunately for Subin, when he was a bit under time pressure in this team, they did not monitor. They monitored the lag, but did not alert on the size of the backlog. They alerted on whether the service was stopping, did not consume events anymore. And the service was consuming events, just not fast enough. Now, even worse, eventually they didn't realize that right away. And eventually, the old events went past the retention time. And that's really becoming a problem because at that point, well, that's too fast. Past the retention time, that means that some events were lost because they were not processed. But they're lucky, they also have a data lake, and so they're able to reconsume the events, improve the service so they can handle more events per second, and then they want to change the monitoring. How do you do that? I think what you should really monitor if you're consuming events, there is one thing you should alert on. You should monitor everything, but you should alert on a backlog that is too big. But what does it mean? Well, there's two options, and then there's a third one. Your first option is to alert on the number of events in the backlog. Right? So if your backlog has more than, 1,000 events, then page the engineer on call and get him to fix it. Now this is nice, but it has one problem, is that if you have a very bursty load for the pattern for the publisher might publish 5,000 events and then nothing for 2 hours. And maybe it's fine to have a high backlog for a while, knowing that you will actually process it very fast. So a better way to do that is time lag. So basically you could look at what is the time between the first event that I have not published, that I have not processed yet, so the next one I have to process, the time it was published, and now. And then you can decide, and this works very nice with typically the kind of SLOs you get for these services, right? In this case, 99% need to be consumed within 1 minute, so maybe it makes sense to have an alert around 1 minute, for example. Maybe a little bit earlier will be better. Now these two ways of measuring lag, they're really nice, but they have one problem, is that they assume that you need to set a threshold somewhere. You need to say, maybe it's 1,000 events, or it's 5,000 events, or 10,000 events. Is it 1 minute? Is it 30 seconds? Is it 1 hour? So it can be difficult for some services, and it is difficult if you want to do bulk monitoring of that, all your consumers. And for that, there's an open source project from LinkedIn that's called Burrow, and it has a very interesting method to monitor lag without having to set a threshold. And we've actually implemented something very similar in Nakad. And it goes kind of like this. You look at the backlog in terms of, let's say, the number of events over a window that you set, maybe 10 minutes. And if at any point the lag was 0, then the state of the particular consumer is okay, everything's fine. If between any 2 consecutive measurements the lag has gone down, then the consumer, at least sometimes, is consuming faster than the publisher is publishing. And so that's also okay. Now, if that is not the case, if the consumer consumes, but the lag stays the same or increases every time between 2 consecutive sample periods, then you're in warning state. Why? Because eventually you're basically getting further and further away from the latest events, and eventually some problems will happen. You will hit the retention time, you will break your SLO. So that's warning. And if at some point you're not consuming anymore, then that's error. And with that, you can very easily find consumers that are lagging behind or that are failing. It doesn't help you if you have strict SLOs, but in general, it's really quite useful. So that's one thing you can do. Certainly, make sure that you monitor the lag. This is the make sure you monitor the lag and basically monitor everything, but make sure you alert on the lag, whether it is with the number of events, the time lag, or a method like Burrow. So okay, Subin fixes the problem. Danny is happy, Subin is happy. Everything is fine. And then, of course, a few months later, something else goes wrong. So, now again. But now, there's another incident. And this one, some customers got more bikes than they ordered. Now, the first one, you had very unhappy customers because they weren't getting their bikes and they weren't getting their order confirmation, actually. This one, you have very happy customers, like, I got 1 bike and I got 2, that's very nice. But that's not exactly a sustainable way to do business, so probably you want to fix something. What happened? Well, again, Subin looks and his team, they look at the service and they see this. They look at the number of events that came in and the number of events that came out of their service, and they see that sometimes there are more bikes shipped, more events out than there were orders received. How can that be? Well, one thing that's very important is that Kafka, Nakadi, and Kinesis all have this at least once guarantee. Every consumer will receive every event once or more than once. There will never be the case that the consumer will not see an event unless they're failed and they're not consuming or they're too late. But if they're consuming normally, they will see all the events. Except that you remember I told you how you consume in Nakadi. Nakadi sends you a bunch of batches of events, and then you have to commit that you are there. There's a timeout for this commit. And if you don't make it by the timeout, then Nakadi will close the connection, and the next time you reconnect, you will get the same set of events because Nakadi has no idea you've processed it. And suddenly, then you have a problem if you did not take that into account. So, of course, there is one thing you need to do. I think this is a well-known thing, but really make sure that your consumer is omnipotent, that it can handle these multiple times, seeing the same event multiple times. And in this case, the blame is not entirely to put on Subin's team, because in fact, since his service is also republishing events, what does that mean? Is that the consumers of that event also should have made sure to deduplicate the similar events. There are many ways to deduplicate events. Probably it's over a window generally, especially when you do stream analysis, stream processing, sorry. But you should do that. That's very important. So again, Subin, Dani fixed the service. The whole team is happy. And I don't know, it's Friday night, they go have a beer. Then comes Saturday. Of course, it's at 3 in the morning. The best incidents always happen at 3 in the morning. I don't know what happens at that time. And there's something, if you're in a company that does e-commerce, you must have heard this before: order drop. The orders are not coming in anymore. Well, in this case, the orders are coming in because, of course, we have our input is the list of orders, but further down the line after the service, there is another one that sends a confirmation and an estimate time of delivery, for example, and that's not coming. So there's a drop. That's really bad. We're losing money, right? Again, what happens? Well, the engineer on call at 3 a.m., sleepy, opens his laptop and checks the monitoring, and what does he see? He sees that, again, the backlog has grown, and you see the backlog is better. It's got like a red line and an orange one that probably alerts you that you're close to the end. And it looks a lot like the backlog in the first incident, right? Except it's not. It's completely different. So that's the thing. For many incidents with an event consumer, you want to get alerted on the backlog that's growing, because that's really what shows you the problems that the user experience. But you want to monitor everything because there's a million things that can cause the backlog to grow. And another thing that's quite popular at Zalando is this case where the engineer goes and checks the bike parts service response time, and he sees that in the beginning, throughout the night and until a bit before 3 a.m., the time stamps are wrong. The responses were HTTP 200, so that was all fine. There's the occasional 500 around like 12:45 and a little bit before 3 o'clock as well. But that's nothing, it just retries. But then at some point, there's no more 200s, and there's only 422, which means what? That probably something like the name of the bike that was ordered is not known by the bike parts service, and therefore you can't have the data to enrich it. What happens? Well, it could be a million reasons for that, but basically you've got to fix it. The point is, the general class of errors you get is you have a dependency that you need to use in order to process your events. And that dependency throws you a non-retrievable error, like a 422. It doesn't know this thing. What do you do? It's basically kind of a poison pill, right? You could skip it, but can you? Maybe the order is important, and then you cannot skip it. So you have a number of options, right? How do you proceed without causing further problems? Well, if the order is not important, but if the order of messages is not important, but each event is important, then you could write to a dead letter queue. Basically create another event type, another topic, and you write there the events that you could not process so that you can continue and process the others, and then you probably have some alerting for someone to look at it maybe on Monday morning or something, and manually process or automatically process the failed events. Now, if the order in which you process the events is not important, and you can tolerate losing events, which probably is not the case here, but if it were the case, then you could just fail, maybe log it or alert on too many failures still, but just continue. And if a partial order is important, then depending on the key that is of importance, so perhaps the customer ID, for example, you might want to have process all the events from a given customer in the same order. Then you'll have to write all the events for this customer into the dead letter queue until you fix the problem and you can do it again. But the others you can process normally. And if really you need a total order, so if every single event needs to be processed exactly in order, then there is nothing else to do but to stop, which is kind of what happened here. Here there was no DLQ. But okay, they can fix the problem. Maybe they decide that this event, they will put it aside, reset the cursor one position later, and then Nakadi sends the next events and everything is fine. And the engineer on call is able to go back to sleep, because by now it's 5 in the morning probably, and he's really tired. So that's what the architecture looks like in the end. So you still have the order processing service that's still talking to the REST API, and it's still reading from orders.incoming, and it's still writing to orders.enriched. But the difference is that it also created orders.enriched to .dlq to have that letter queue. By the way, this is something I've heard quite a lot at Zalando. People say, oh, does Nakadi support the letter queues? Probably you could ask the same question. Does Kafka support the letter queues? The answer is yes. It's just another event type, or it's just another topic. Just create another one and decide, this is my letter queue. That's where I will publish my messages. There's nothing particularly special about the letter queue. It's just another one of these, right? All right, so we've had 3 incidents now, and we've got a much better service. The number of middle of the night calls, or even middle of business day for matters, have gone down quite significantly, and everyone's happy. Subin did a great job. Danny's very happy, and maybe Subin gets promoted. No, it's gonna be nice. So now I want to sort of wrap it up. We have these 3 big incidents that are actually among the 3 incidents that happened the most in the incidents that we have seen at Zalando that are related to Nakadi. So these things in practice, they really do happen, and they do happen quite a lot. So what do you need to do? We've already talked about it actually. First, monitor everything. This is really important. And alert on lag. I think if you alert on lag, you will solve the vast majority of your problems, and you will not be alerted for things that are not very important. You'll only be alerted on things that will affect your customer. For the lag, you choose the number of events, time, or the borrow method, as you wish. And make your consumer identity. This is very important. Also, very important, monitor business processes. There are a lot of business processes out there that involve several services that have to move data from one place to the other and enrich it in some way, and it gets, sometimes you want to monitor them. So for example, one way of monitoring the business processes is to check that the number of orders that are placed on the website and the number of assembly orders that are sent to the factory are the same. That would be nice with a period of a few minutes, for example. That's how we found the incident number 2, right? Where there were too many orders, and that was not normal. Business process monitoring is also very, very important. It's really hard to find these sort of problems if you only monitor each service individually, right? And finally, most of all, know the services you use. Each of these services, be it Kafka, be it Kinesis, be it Nakadi, they have limits, they have guarantees, they have SLOs, and they have funny ways of failing that can be very subtle, and you will learn about them eventually. You will either learn about them because you did the homework ahead of time, or you will learn about them because there will be an incident. So you can learn about it by reading the documentation, by reading past incidents, by talking to your colleagues, by reading, I don't know, blogs, videos, anything, maybe attending this talk. Hopefully that will also be helpful. My point is, it's not always as easy as it looks in the tutorial. There's a lot of great things about event-driven systems, but there's also some complexity that I think you should be aware of. So that's the end of my talk. There is a link to Nakadi. I'll write sort of a wrap-up of this talk on my blog at some point. You can check it out there. And if you have any questions, please go ahead. Thank you.
Perfect. Thank you for that. Does anyone have any questions that they want to ask now while it's all fresh?
I have a little question, but it's a bit difficult because I have no experience with event streaming, but I find this concept very interesting. But I was asking me all the time, how do you secure that you don't lose any data? Or let me say, you have some consumers, the consumer consumes the event, but how do you know that the consumer also sends something back to the next consumer and so on, that the whole workflow is working?
Yeah, so if I understand your question, so making sure that the consumer consumes all the events, you do that by looking at the lab, right? Because you need to write your consumer correctly as well. So that this is a very good one. It's an incident that doesn't happen often, but it has happened before. As I said, you get a batch of events, let's say like 10 events from Nakadi, and then you process them, and then you tell Nakadi, I'm done, I've done these. If your consumer commits before it has actually processed all the events, if it has to put them in the database before you've actually committed the transaction, then it is possible that you will tell Nakadi that you're done before you're actually done, and something will go wrong and you have lost your events. So that's one of the first things you can do. But I think your question was more general about several rounds of consumers that we publish that is then consumed by someone else that is published again. I think we get into the area of business process monitoring at that point. So you should, in addition to monitoring individual services, but I think this is also valid for REST APIs or anything else, you should monitor that the whole flow of the whole process of maybe an order or a user joining or I don't know, anything else also makes sense, right? So make sure that there are no more bicycles coming out of the factory than bicycles that are ordered. Make sure that every order actually has a payment in the end, these sort of things. Did that answer your question?
Yeah, it's more like, let's say someone orders a bike, and some consumers know about it, and then the customer thinks about, oh no, I don't want the bike, and cancels it, and the consumer started processing, but you don't want to process it anymore. And so I don't understand how this works when you have a queue with a lot of events, and this cancel event is very important, but it may come pretty late. So everyone processed it already, and there's no chance to go back, right?
Well, that kind of depends. So this is something that can happen quite a lot. You will have events that create an order, and then there'll be some bunch of others, and then eventually later there's an event that cancels an order. Then you have, in principle, an event that cancels an order could happen at an arbitrary amount of time in the future, right? 5 minutes later, 10 minutes later, 2 hours later. So you first have to decide that, okay, after X time, can't cancel anymore. There's two ways you can go around it. First, you can build your consumers and publishers in a way that they will be able to process all the events. So for example, you process the creation of the order, and will add the order to your database, and then later you'll process the cancellation of the order, and it will remove the order from the database. But maybe what you want to do sometimes, and it's actually quite a common pattern, and you want to give kind of a grace period of, let's say, 10 minutes. Then you can do event processing on a window of 10 minutes to say, well, whenever I see order created, I kind of open a window of 10 minutes during which I see coming a cancellation event, for this particular order. In which case, I will not persist the event in the database. Or probably will persist it somewhere, then move it or commit after the window has closed. So you could use windows, or you could build your workflow in such a way that it can just be cancelled. Okay. So maybe you will say like, well, the orders will only be sent to the factory floor after half an hour, because you have half an hour to cancel it. And afterwards, if you want to cancel it, well, there will be a cost to it.
Okay. Yeah.
I have a question, Lionel. My question is specific to idempotency of consumer. So can we make consumer idempotent all the time? So let's say, for example, I want to count the number of orders for a product in real time. In this case, I will be batching the orders and grouping it by order, I mean product ID, and then updating the count. So in this case, if I lose the commit offset for one batch, I'll be recounting that orders again, right?
Yeah, you could, on principle, you could do even something for arbitrary amount of time, but generally these things, they happen fairly quickly, right? You'll miss a commit, so you'll get the data again. And you could generally define a window of time that you find is acceptable, that it's very unlikely that there will be a duplicate coming afterwards, for example. And then you can deduplicate over this window of time. And your window could be infinite if, for example, in the case of your order and you want to count the orders, if you put the order ID in some sort of storage, fast read, fast write storage, like maybe an in-memory database, then every time you get a new order, you can just check whether it's there already and then you count it. But typically you would want eviction policy for that. And I think if you set a sufficiently large time window, then you're probably fine. And just in case, you might want to have something to reconcile double orders. But then there's a point where if you get 1 million orders and 1 every 1 million is a duplicate, maybe it's not as bad. Depends on the size of the order, of course.
Okay, so these issues happens while rebalancing, the partition rebalancing. And I'm facing this issue, and in my case, instead of this order event, it's add impression. So my pipeline is streaming pipeline is directly tied to revenue and billing.
So yeah, if you have partitions being rebalanced, so for everyone, maybe some people are not so familiar, like Anya, for example, with event streaming. So usually in an event type or in the topic, you have a number of partitions. And you can have as many consumers as you have partitions. And that's how you can kind of grow your throughput, is by adding more partitions. And then the problem is, when a new consumer joins or a consumer leaves, the streaming platform will reassign which partitions go to which consumer.
Yeah.
Generally. And then you could be in a situation where, well, you have a consumer, you saw one order and it failed to process it, but it counted it. And then, but just at that moment, rebalance happens and it's another consumer that sees the order and it doesn't know that the first one had seen it, so it counts it double. Right? Is that the situation you're referring to?
Yes, same situation.
Yeah, you have a number of things. So you can either have a cache that is common to all of them, you have a Redis database or something, or at least in the case of Nakadi, you can actually tell Nakadi, I want to consume this particular partition or this set of partitions. And that's really useful in the case where you want all the events with the same key to be consumed by the same consumer, like for that example.
But in this case also, while partition rebalancing, let's say I'm consumer A, I'm reading from partition A, and then consumer B left the group, and then C rejoined. Then the consumer A might not get the same partition A, right?
So what I'm saying is Nakadi has this feature. The consumer A can say, give me partition A and nothing else. Consumer B says, give me partition B and nothing else. Now, when A leaves, B does not get partition A. It's just waiting. And when A comes back, it gets its partition again.
Cool. Yeah, I'll surely check out Nakadi.
But thank you for that. That was great. So yes, I'll pass it on to Peter.
Hello everyone, my name is Peter. I will have a talk that will be substantially less technical than Lionel's. It will be more about managing a team of data engineers and how it comes together with some practices that are nowadays very common in DevOps. First, a little bit about me. I am currently a data engineering team lead at Quandoo, which is a restaurant reservation platform. I worked as engineering lead and as a data engineer and backend developer at various startups, consultancies and bigger corporations before. By education, I'm a physicist, but I've been working in IT for about 15 years. In this presentation, I will first define some terms. Namely, I will talk about who I talk about when I talk about data engineers, because in this room, I assume there are many different people that, or many different types of people that all work with data, and they all work slightly differently and use slightly different skills. So when I'm talking about data engineers, first I would like to define who I'm talking about. Then I will talk about what I'm talking about when I I'm talking about a well-functioning team, especially in tech. This is usually kind of implicitly defined, but it can get quite complicated when some of your inputs or some of your stakeholders are not entirely well defined, which can be the case in data engineering teams quite often. I will tell you why I think data engineering is actually more similar to DevOps than to software engineering, and which best practices we can use to satisfy the stakeholders that we have and their stakeholders. And finally, how it all comes together. So the purpose of this presentation would be to just sum it up, to introduce a vision of a well-functioning data engineering team. So the first part, let's go into what data engineering is, then what well-functioning is, and finally, let's put the vision together. When I'm talking about data, or when we talk about people that work with data in companies, I like to distinguish several groups of them. I like to talk about business analysts. These are typically people that present the data, that talk to managers, that prepare reports. They should understand very well the business logic, how processes such as revenue calculation work. They use terms such as lifetime value or click-through rate, conversion rates, and so on. Their skills can be wildly varying. It can be anyone from a working student that uses Excel to calculate something to even some specialized and expensive consultant that will look into business processes and try to use data to reason about them. Their stakeholders are mostly managers and product people that develop products and so on. The data scientist is another group of people in my eyes. These are the people that are more focused on the advanced methods and advanced computational processes that we use that are used to process the data and to analyze data. The emphasis for these people is on these processes rather than on presenting the data, and they will mostly work with, they will be coding, they will be using big data, they will be writing the databases. They cannot use Excel anymore. But the stakeholders for these people are mostly the same as for business analysts. They will also talk to the product developer, they also need to understand business processes and so on. And finally, data engineers are the people that are closest to software engineers. They are people that many of us, including me, confuse with software engineers because 90% of time is spent by writing some software, or 90% of time that these people consider useful is spent by writing the software. They manage data warehouse structure, they manage ETL pipelines, they set up Kubernetes jobs and so on. They focus on the technical task with regards to data management, and they mostly talk to the previous two groups. That means they rarely talk to the manager or other than their own manager, but they will rather present their data through someone else. The good hint that you are a data engineer is that you are trying to automate everything, and that you will spend time rather on automating a script or writing a script that can run remotely, while the typical data scientist or business analyst will write a script that will just run on their laptop once and then present the results. One word of caution here is that although their responsibilities mostly overlap and they can be working quite often on the same kind of task, they are good at different kinds of things. Data engineers are typically better at coding, while business analysts are typically better at presenting. And this can lead to some funny situations when you try to task these people with the task that the other group should handle. It can end up with in rather interesting situation. I've seen very good data engineers preparing reports for top management, which they send out as a CSV file. And let's just say that it took longer to explain the end recipients of this report how to change the decimal comma to decimal point in their Excel to open this file, than it took to prepare the report itself. And there was nothing wrong with these people. They were really skilled. They were just, this was just not their skill set to present this data. And conversely, I've seen a very good data scientist prepare data processing pipelines. And these data processing pipelines looked like that there was Jupyter notebook server, and IPython notebook was run on it once a week, which filled Salesforce database, and there was some complicated business process hang on it. And it can take months to disentangle processes that were written like this. Again, it was very skilled data scientist, just he was doing something that was clearly out of his comfort zone. And so this is the reason why I like to distinguish these people. So in the rest of my presentation, I'll be focusing on the team of data engineers. They're mostly these people that spend their time coding. Now, when we talked about what data engineers are, I'd like to specify a little bit what I mean when I talk about a reliable system. The system can be anything. It can be an app, it can be a website, or it can be an ETL pipeline. And we will see it may not be even easy to define what inputs and outputs and what are and who the users are. So when we talk about reliability, it's just some sort of guarantee that the user always gets a correct output from the system that we manage, no matter what inputs and outputs, no matter what inputs they give. So if they give a wrong input, they should get an error. They should not get some nonsense answer, and that is especially true when your system is a database. So let's break it down a little. Software engineers, and this is how I used to see data engineers before too, typically write some code and they work with some pre-existing data, or they create some data based on the inputs that the user gave. So take input, we mix it with data, we do some magic in the code, we return something back. Optionally, we will write something else to the database. When we want to guarantee that everything runs smoothly, we can test our system by guaranteeing that all the outputs are correct, right? So we have under our control the data, the code, and the output, because the code is just providing the output. We can go as far as automating it and just providing some testing inputs and simulating as many of them as we can. We can have some staging data, and we can just test that whatever change we do to the code will provide reasonable output. That's a process that's relatively well handled, and most software engineers are comfortable with it by now. How does it work with data processing pipelines? So we have some data. This data can come from some API. It can be a weather database API, which is public, or it can be currency exchange rates. It can be a tracking data, which is partially provided by other parts of the system that you have. And then we write some processing pipelines which load this data, and they produce some more data. They write this data to database or data warehouse. Now, what is the input of this thing? What is the output? Is the inputs just data and the output is the data again? And actually, who is the user then? How is this data used? Where do our requests come from? The data that we output can be an upload to an FTP server of our client. It can be something else. It can be a downloadable link. It can be just a table in a database, which is the most common thing. In any case, it's kind of hard to distinguish what is what here. So one answer that I used to consider for a long time, which turned out to be spectacularly wrong, was that our user is analyst, because these are the people that we most often talk to. The analysts or the people in business intelligence team, they come to us and they request us, hey, we need to have in database data from here, it needs to be in this format, or we need to take data from somewhere else, process it somehow, and output it somewhere else. So so I consider analysts logically our stakeholders, and I tried to provide treat them as our users. And their requests were kind of input, but what their requests were, it was kind of SQL code, which is very complicated input to, it is too complicated to treat as an input. And still, the outputs of the code that we wrote was something that they didn't interact with directly. So it was rather hard to treat in this way. To find out how it actually looks like, we need to take a look at the previous picture. It was rather incomplete. It was not just the code and the data. This code runs on some server. The data is stored at some databases, and all these things are treated by software engineers as resources. So the user is typically a customer. The software engineers write the code, and there is a different group of people that treats the resources on which this code runs, and these are the DevOps engineers. Now, when we look from this perspective at what the data engineering team typically does, it turns out that the data engineering team has very similar position. Analysts and data scientists are not really our end users, but their stakeholders are, in the same sense as the customers are end stakeholders for a DevOps team. Although DevOps doesn't typically interact with the customer, what they do directly affects customer. So the same way what data engineering team does directly affects stakeholders of business analysts. What we manage, what data engineers manage, should not be treated as a software product. It should be treated as infrastructure. And data produced by ETL pipelines is not an output. This is simply a resource. And the funny part in this whole picture is that the products or the software products are actually dashboards or reports that analysts produce. The analysts are the coders, and their SQL queries typically are the code which they write. And the data engineers just play the same role as DevOps. From this perspective, the business analysts and should treat us the same as DevOps. So, and that's why data engineers should approach managing and testing their products or their ETL pipelines, their data warehouse in the very same way as DevOps approaches managing the infrastructure. And even more, the data warehouse is rather similar to a cloud service rather than to classical infrastructure. While today it's still possible to see DevOps that manage actual servers, it's more and more common to outsource this as a service and just use the infrastructure as a service. And this is exactly what data engineering does. When a business analyst needs to handle the data, they are not interested on what database it runs. They are only interested in having ability to do their job. And the service that is enabling them to do just that is provided by data engineering. From this perspective, testing ETL software makes about as much sense for data engineer as testing Terraform templates or CI/CD pipelines would for DevOps engineer. It's not that we should not test it, it cannot be tested, but it's not the primary thing that we should test. The method that is nowadays used or is very popular for guaranteeing a quality infrastructure is called service reliability engineering. And this is a method that I would like to go over the basic I would like to go over the basics of this method, since this is a data meetup rather than the SRE meetup. On this particular meetup, I would like to explain at least a few key, or from my perspective, key terms in this method of managing, and these are service level indicators. They can be thought about as an on-off switches or indicator lights which tell that the service is operating correctly. Then I would like to introduce an incident handling and some terms that are used in SRE for incident handling and how they help us to satisfy our stakeholders better. Then I would talk about service metrics and which service metrics we can use actually in data engineering, what the service level objective is and what the service level agreement is and what should we do or how we should behave when we breach them. And finally, how error budgets can be used in in a more efficient management of a data engineering team. The first of these terms is service level indicator. In the traditional DevOps, this would be something such as latency or even accessibility of a given service. In data, this would be rather hard to define, since our output can be a table in a database, but the set of metrics that is typically used in data engineering is, or one of the more common sets of metrics is called 6Ds. These are data accuracy, completeness, uniqueness, consistency, recency, and timeliness. The examples for each of these are rather easy to find with respect to the last one. For example, for data accuracy, we could say that the data that we fill into database is really the data that the analyst expects it to be. The breach of this agreement would be if we would, for example, swap two columns in a database. It's an error that happens actually quite often. Data completeness is the no records are missing. If we skip a data import, because for example our process breaks, then the yesterday's reservations might not be filled in a reporting dashboard, or we might not import all of our tracking data and it looked like we have a dip in a traffic. Uniqueness would be a duplicate report. So that's the essentially opposite of the completeness. When we run our data import twice and we don't have check for it in a database, we could import twice as much data. So we could see, for example, it could seem, for example, that we had twice as many visitors. Consistency is that the info means that the info in different tables in the database is the same. The same info in different tables in the database is the same. So if we have, for example, number of customers, and we look in one table that contains customers, these numbers should be the same as in another. They might be these two tables might be generated by different processes, and one of them might fail. In that case, we get incomplete and at the same time inconsistent data. Recency has to do with how often we actually update our data, and timeliness is a kind of combination of recency. It's essentially, it can be considered as a recency. It's rather hard to explain, but it can be explained as a schedule being good enough for a given task. For example, if we need our data to be updated or if we use our dashboard to, say, call restaurants and notify them of the new reservations, then it is not good if parts of our ETL pipeline produce data that will only show new reservations every 6 hours, because by that time the shift in the restaurant might be over. A nice property of all those metrics is that the tests for them can be automated, and the tests, the automated tests for these metrics should be actually part of a definition of done, and they should be designed together with our stakeholder. That means analysts or the data scientists that use the data should agree on what the criteria are that the data in the tables is good. So your data quality is only reliable as your tests, and that's why all these tests should be automated. There are many ways how it can be done. At Quandoo we use a tool called dbt to do a lot of transformations in our data warehouse solution, which is BigQuery. And this can be used also to, among other things, to write tests for the data. So for example, for accuracy, we can write a test which will guarantee that at least the columns in the table have the correct type, that they don't have some nonsense values. And this is the kind of test that should be agreed on by the time when we finish deploying the new table into the data warehouse. An example of uniqueness can be a different test, which is in dbt called custom query test. So, on this example is a custom query that would just count duplicate records in our table. and outputs all unusual rows. In ideal case, we should not get any output from this query. If we do, we should raise an alert. That means that, for example, the process that imports orders into our system ran twice. Finally, the status of our tables can be should be displayed to all interested stakeholders in the same way as the status of any other service. Here is a small comparison between the AWS service status dashboard and Quandoo data warehouse dashboard, which displays the status of our reporting table. There is one bonus information compared to the AWS status in this dashboard, and that is the recency of the data. Because this one is the most commonly, this used to be the metrics that we most commonly failed, and it was very useful for analysts to be able to see that all processes ran on schedule when and all tables were filled as they expected them. The other thing to take care about is to use alerts sparingly. We can have a dashboard which shows status, but this dashboard can be checked by analysts, but we should not send alerts immediately when anything is red on this dashboard. We should check this dashboard every morning when we come, but we should only create alerts for things that are really important, and that is something that any DevOps engineer, essentially any software engineer, will tell you about. The moment you start alerting on everything, your alerts don't make any sense. Now, what happens when something on this dashboard becomes red? So that means one of our data engineers came to work, they check the dashboard, which they get sent by email every morning, and they see some of the tables were not updated. Or we can have a slightly more complicated situation when someone points out a problem in our data. So like analyst comes to us and says that this data is not correct because there is a problem for which we do not have tests yet. What should we do then? This is something that we need to handle separately. For that we have a separate procedure which is called incident handling. The important parts of this procedure is to have some report which should be very well communicated to and to which you can refer later to understand what actually happened. It can be post-mortem. There are different ways to write them, and there should be always a person which will push everyone around to complete all parts of the incident handling. And these parts are the reporting. This can be done either internally when someone checks the dashboard and then reports incident, or externally when someone tells us that there is a problem with our data. And the important part here is that this reporting should be handled in a single channel. It does not help if someone reports problems to you by Slack, another person by email, and another person just comes to you in person. There should be just one channel where everyone can see that. Otherwise, you will receive reports from multiple people about the same problem or the problems that are related to it. And at the same time, when we find an incident in the data, this should be reported in the same channel. The way we do it is that we create a ticket on our Jira board, which has a separate incident type, and we use a Jira Slack integration. So then there is a Slack channel where everyone can see, yes, today there is a problem with some tables, and my reports are using these tables, so they don't have to come to us and ask, hey, why my report is showing me numbers that do not make sense. This helps to decrease load of this request immensely. Verify and describe. Once the problem is found, it is not enough that we understand what the problem is. Even if it's something obvious, we should always add the description. And the incident commander is the person that should be responsible for each problem having such a description. It happened several times that a person reported an incident, something like reservations do not seem correct, which did not have any description, and then they went on holiday. This really does not help. It's really important that anyone in the team can pick up on any problem, and clear description is a big part of that. For prioritizing, is like, okay, when multiple incidents happen at the same time, it is important to know which ones are should be resolved first. And in order to do that, it is very good if you have some idea of how your data is used. If you don't know that the table is used in a critical report, then you don't know that the table is important. Keep track of your data usage for prioritization. Typically the more reports or the more important reports the table is used, the more high priority incidents with that table are. Then resolving, as I said, there should be more people, or anyone should be able to pick up on the ticket, even if they are not intimately familiar with the system. They should at least know who to contact or where to start investigating an issue. And finally, documenting and listing contributing causes, both technical and non-technical. What caused the issue? What was the time to detection? And how long did it take us to resolve that? If we collect all this information in the end, then we can do something with it. If we don't, incident handling are just coming and going. Finally, a few tips. As I said, have a single channel for your stakeholders to report incident. Have a single place to collect the status and report status on each of them. In our case, this is a Jira board. And the updates should be sent over the same channel where the incidents are reported, so that we don't have a duplicate report. Finally, understand relative importance, that I also mentioned, who uses the tables and how. If we don't know that, we don't know how important it is, and we might spend time on resolving data outages in data that is not used at all, and resolve later data that is actually critical for business reporting. Be really adamant about descriptions and post-mortems, and this is the task of the incident commander, which should be some person that will chase people to write the good descriptions and write good descriptions of the resolutions. And that's it. Then having the dedicated person to make sure that the rules are followed is not necessarily the same, is not strictly necessary, but then it will end up on you or on whoever has to work with the incident later. If we follow all these rules about the incidents, then we can calculate the most important metrics for the data. So for classical services, these metrics could be something, the percentage of time the service is up, or the percentage of time when the latency of the service is under some threshold. In data engineering, we use something which we call data downtime. And it is simply sum of time during which the tables in our data warehouse were not as they should be. This time should be calculated for incident of each severity separately. That means if we have a lot of low severity incidents, it might not be as bad as when we have a lot of high severity incidents. But all incidents at a given level of severity should be the same, should be treated the same. This metric can be calculated for every sprint or any given period of time that you use in your planning. And there are also other indicators such as number of incidents, average time to detection, and so on, which are also important. But this one is the one which typically matters most to our stakeholder and affects most their stakeholder. Once you define your metric, which can be data downtime, then you can define your service level objectives and agreements. The difference between these two is that the service level objective is a value of the metrics for which you are aiming for, and agreement is a value that you promise to your stakeholder, so that they can deliver their promises to their stakeholders. The good trick here is that your objective should be much lower value than the value that you promise to your stakeholders, because if it's not, then any time you break your contract, break your contract with them, someone's gonna be very angry at you. The service level objective is used in a different way than service level agreement. And how it is used, I will explain now. So basically, you have two different type of tasks that you can handle in the team. One is extending the functionality and, for example, adding more tables, adding more data ingestion processes, adding more processes that create a new data marts. That means they read data from the tables that you already have and they produce new ones. And refining these features, adding access control, and so on. These are the new things that people ask you to do. Type 2 task would be improving the functionality that you already have. This can be code refactoring, splitting some code from shared code from multiple processes that you wrote on a deadline and writing a library for it, automating things that you often have to do manually, and last but not least, cleaning up. As I said, you should keep track of the data that you use, and if you don't, you can easily end up in a situation when you end up managing a lot of data that nobody is using anymore. So cleaning up is also part of improving data warehouse functionality because it decreases the load of work that you have. And whenever you deal with a team of people that behave like software engineers, these people try to automate everything, as I mentioned before, and this leads to a lot of requests for work that you are not sure is useful. For example, you have a request for a new data mart or a new data ingestion process from some other stakeholder, but your engineers tell you, hey, but if you allow us 2 days to refactor this data ingestion, then we are gonna be able to accomplish this task in half of the time that they would take us now. And the next time task like this comes, we can do it even faster. What should we be working on? This is the answer that another term from the SRE can answer, and this term is error budget. In order to make informed decisions about what types of tasks you should focus on, you should use your service level objective and your metric value. The difference between these two is your error budget. The moment you get under you are under your SLO and you are providing a service for which you aim for, you can focus on refactoring. Or you can focus on adding more features. The moment you are over your SLO, you exceeded your error budget for adding new features, and you might want to focus more on improving things that you already have. You haven't breached your service level agreement, so you haven't breached the promise you have to your stakeholders yet. But at the same time, you're able to decide on what kind of task you should focus on next. So if we use our data downtime, that means if we measure how big fraction of the time the tables that we promise to our stakeholders are filled with the data as they expected, and we set some number on this expectation, we can easily decide whether we should keep adding new tables, or we should, for example, start removing some tables which are not used anymore, or refactoring our code, or automating things that go wrong. So some summary, how it all comes together. So also data engineers work much like software developers. From the usage of their work, they are more similar to DevOps. The terms important for management of their work are service level indicators, objectives, and agreements. We should use automated tests, which should be developed together with business analysts to determine our service level indicators. And we should communicate the status of our data very clearly and have a very clear procedures on how to handle incidents when something goes wrong, because it will. And these procedures can help us to calculate our basic metrics, which can be data downtime. We should have some expectation on what the data downtime should be, and we should be able to promise certain level of accessibility to data to our stakeholders. And finally, how high below or under our expectations, our objective we are, can help us to decide on what type of task we can focus on when developing the data warehouse further. That would be all. Thank you.